the next law, which is usually called as law of multiple proportions. Law of multiple proportions meaning is two elements will be combining to produce more than one chemical compound. For example, I am taking here hydrogen combining with oxygen to produce water is the first reaction. The same hydrogen and oxygen, if they combine in a different proportion by weight, can produce even hydrogen peroxide also. Means that two elements combine to produce more than one chemical compound. For such type of chemical compounds, this discussion will be very helpful, which is called as law of multiple proportions. This is proposed by John Dalton. According to him, if two elements combine to form more than one chemical compound, then the different masses of the reactants, masses of the elements that combine with a fixed mass of the other element bear a simple ratio to one another. Best example that can be illustrated by taking the same which I proposed, water and hydrogen peroxide both are being produced. Please see the weight composition in that. 2 grams of hydrogen is combining with 16 grams of oxygen in the form of water. In the form of hydrogen peroxide, when the compound is produced, the same 2 grams of hydrogen combined with 32 grams of oxygen. Please remember that in both cases, my calculation is per 2 grams of hydrogen only. 2 grams of hydrogen only I made the calculation. What is the weight of oxygen in both the chemical compounds? 16:32, which is equal to 1:2, which is a simple ratio. So, the weight of oxygen that combine with a fixed weight of hydrogen bear a simple ratio. That simple ratio is 1:2. What is a simple ratio? A simple ratio can be 1:1, 1:2, 2:3, 3:2. Like that, ratios are usually called as simple ratios. But please remember, you need to fix the weight of one element. Then you need to make a verification of the weight of the other element that is going to produce two different chemical compounds. Let us verify this with the help of one more example. Nitrogen and oxygen will be combining. Nitrogen and oxygen, when combined, it produces 5 different chemical compounds. I make a list of them. The first one is nitric oxide. This is nitric oxide. Next one is N2O, which is nitrous oxide. Then will be N2O3, called as dinitrogen trioxide. Next will be NO2, nitrogen dioxide, and the last one N2O5, dinitrogen pentoxide. Like this, 5 different oxides are possible. Same nitrogen and oxygen combining to produce 5 different chemical compounds: nitric oxide, nitrous oxide, dinitrogen trioxide, nitrogen dioxide, and nitrogen pentoxide. For convenience, what I do is, I change this proportion. This is N2O2, which is nothing but NO. Then will be N2O, then will be N2O3, then will be N2O4, which can also be written as NO2, and this will be N2O5. Please remember that N2 is common in all of them. N2 is common in all of them. If I fix the weight of nitrogen, the oxygen, weight of oxygens combining, if I take the ratio, you can prove the law of multiple proportions. So, for that, please observe here N2O, nitrogen oxygen combining ratio 28:16. N2O4, nitrogen oxygen combining ratio 28:64. NO 14:16. N2O3 28:48. N2O5 28:80. In this order, if you are going to present all of them, in all of them, weight of nitrogen is fixed. With 28 grams, you fix all the masses. you can make a verification that they are supposed to be 8 is to 16 is to 24 is to 32 and 40 respectively. Means that for every 14 parts of nitrogen, the oxygen combining will be 8 is to 16 is to 24 is to 32 is to 40, which is equal to 1 is to 2 is to 3 is to 4 is to 5. Means that fix the weight of nitrogen and go to the calculation of what amount of oxygen will be combining. 14 parts by weight of nitrogen is combining with how many parts of oxygen by weight. So, these are oxygen weights in all the chemical compounds. You can take the ratio. If you want here, you can raise this quantity because all of them N2O, N2O4, N2O3, N2O5, I write this as N2O2 or 2NO can be written. It will be equal to 28 is to 32. Now you can take the ratio 28 is to 16, 28 is to 32, 28 is to 48, 28 is to 64, 28 is to 80. 28 is fixed and the remaining, if you are taking the ratio, it will be equal to 16 is to 32 is to 48 is to 64 is to 80, which will be in the ratio of 1 is to 2 is to 3 is to 4 is to 5. Okay, with a fixed weight of one element, the other element which is going to combine bear a simple ratio. Example 3, sulfur combines with oxygen to form two oxides. One is sulfur dioxide, the other is sulfur trioxide. In this case, I can write here sulfur quantity will be 32 grams of sulfur is going to combine with 32 grams of oxygen in the first oxide. In the second oxide, 32 grams of sulfur is going to combine with oxygen quantity will be 48 grams of oxygen. I made here in both cases 32 grams of sulfur only. With a fixed weight of sulfur, what is the ratio of the oxygens combining? Their combining ratio will be 32 is to 48. Okay. With 16, if we are going to divide, it will be 2 is to 3 mass ratio, which will be a simple ratio. I take one more example for solving. The example is taken, hydrogen peroxide and water contain 5.93% and 11.2% of hydrogen respectively. Show that the data illustrate law of multiple proportions. For example, hydrogen peroxide compound is given. Hydrogen peroxide and water contain 5.93. So, hydrogen quantity will be 5.93. Automatically, oxygen quantity will be equal to 100 minus 5.93. So, that is being written here. Similarly, in the other case, hydrogen quantity is given as 11.2. Oxygen quantity, because he mentioned this as percentage, means that per every 100 grams of the compound given. So, therefore, it will be 100 minus 11.2, which will be referring to this quantity 88.8. Now, please observe here, in the first compound hydrogen oxygen combining ratio, mass ratio 5.93 is to 94.07. I want to make it per 1 gram of the substance. So, take the smallest number and go for division. So, in this case hydrogen oxygen combining ratio will be 1 is to 15.86, and in the second one compound water, if I am taking here smallest number, I am taking 11.2, divide both of them, so that you are going to get with 1 gram of hydrogen how much grams of oxygen will be combining, which will be 1 is to 7.92. In both the cases, I fixed the weight of hydrogen. So, weight of oxygen that are combining will be in the ratio of 15.86 to 7.92, which is equal to 2 is to 1 ratio, which is a simple ratio. Let us look into one more example. A hypothetical compound, often in the examination, hypothetical compounds, imaginary compounds may also become a discussion. He don't give you the original name of the compound. Carbon combines with hydrogen in PQR, means that P is one compound, Q is another compound, R is another compound. The percentage of hydrogen in PQR are being given. In P, 25%, in Q 14.3%, in R 7.7% of hydrogen is being given. You are asked to calculate, or you are asked to show whether this, which law is obeyed by this. For the solution, as percentages are given, whenever percentages are given, the weight percent of one element is subtracted from 100 so that I can get the weight percent of the other. Hydrogen is given 25, so carbon I calculated 75. In the second compound, hydrogen percentage is given as 14.3, I calculated for carbon, it will be 85.7. In the third one, it is given that it is 7.7%, so 92.3 will be the mass percentage of carbon atom. I need to fix the weight of hydrogen. So, in all of them, per 1 gram I made the calculation. Per 1 gram 75 by 25, meaning is 1:3. In this case 1:6, in this case 1:12. So, I fixed the weight of hydrogen with 1 gram of hydrogen. How much grams of carbon are going to combine? They are combining in 3:6:12 ratio. 3:6:12 will be equal to 1:2:4 ratio, which will be a simple ratio. So, therefore, this law is in accordance with law of multiple proportions. Okay. After the third law, a little bit complicated case we are going to consider. This is usually called as law of reciprocal proportions. Law of reciprocal proportions was proposed by Richer, and this law states that when two elements combine separately with a fixed mass of the third element, hypothetical elements are being taken. Now let us consider the chemical compound formations. Element A is combining with B to produce the compound AB. Similarly, element C is combining with B to produce the compound BC. With a fixed weight of B, A and C are combining, let us suppose. With a fixed weight of B, the two elements are combining. If they combine to produce a chemical compound AC, they also bear the same ratio or multiples of it, or simple ratio of it. So, when two elements combine separately with a fixed mass of the third element, then the ratio of their masses in which they do so, means that in which they combine, is also either the same or some whole number multiple of it in ratio which they combine directly of each other. Instead of this hypothetical example, let us consider here one important case. Let me say that calcium is an element which will be combining with hydrogen to produce calcium hydride. Calcium also combine with chlorine to produce calcium chloride. Suppose if hydrogen and chlorine combine to produce HCl, the two elements hydrogen and chlorine, when they are combining with a fixed mass of calcium with a fixed mass of the third element, a ratio will be maintained. The same ratio will be maintained even in the case of HCl formation also. This is a hypothetical example and this is a specific example. Let us go to some of the models here. Before going to that, let us see the explanation what is given here. Consider A, B and C are three elements. A plus B combined to give AB. B plus C combined to give BC. If the mass of B is fixed, means that this middle element mass is fixed. With a fixed mass of this, what are these elements weights combining? The same weight ratio is maintained even in the formation of chemical compound AC. So, that is to be illustrated. Yes, students, let us look into a specific example I am taking here. Carbon combined with oxygen to produce carbon dioxide. Sulfur, another element, combined with the same oxygen to produce sulfur dioxide. So, two different compounds are produced. A third element, oxygen, is going to combine with sulfur individually and carbon individually to produce two different chemical compounds. So, in carbon dioxide, I am taking the weight ratio 12 grams of carbon combined with 32 grams of oxygen. The same thing for sulfur dioxide, 32 grams of sulfur is combining with 32 grams of oxygen. So, if I present this information in carbon dioxide, carbon oxygen mass ratio will be 12:32. In sulfur dioxide, sulfur oxygen mass ratio is 32:32. What I am doing is, with a fixed weight of oxygen, what are the weights of carbon and sulfur combining? I am fixing the weight of oxygen, that is 32 grams of oxygen in the first case and 32 grams of oxygen in the second case also. If I am fixing this, the weight of carbon and sulfur combining with a fixed weight of oxygen are in the ratio 12:32. So, I am going to get the ratio 12:32, and surprisingly the same ratio is also maintained even in the formation of sulfur dioxide also. In sulfur dioxide, every 12 grams of carbon combined with 64 grams of oxygen. Now, I am comparing both these two in both cases. For example, in the first case where I made this calculation from this data, carbon to sulfur ratio will be 12:32. In the compound formation of carbon disulfide, okay, in carbon disulfide formation, every 12 grams of carbon is combining with 64 grams of sulfur. Yes, carbon to sulfur ratio is 12/64, one is 12/32, another is 12/64. If I take the ratio, that will be a simple ratio. In some cases, maybe 1:1, in some cases multiples of it also, and this ratio is found to be a simple ratio. Yes, if you are able to understand that, we go to the second example. I am taking here another such combination, carbon and hydrogen combining to produce methane, carbon and oxygen combining to produce carbon dioxide. Means that hydrogen and oxygen are combining with a third element, carbon. Okay. So, the weights of hydrogen and oxygen that combine with the third element, carbon, will bear a ratio, that is also a ratio in which these hydrogen and oxygen are combining to produce water or a multiple of it. So, for that I made the verification, CH4 molecule is taken. Every 12 grams of carbon is combining with 4 grams of hydrogen. In carbon dioxide, 12 grams of carbon is combining with 32 grams of oxygen. I am going to fix the carbon weight. With a fixed weight of carbon, what are hydrogen and oxygen combining? Their mass ratio will be 4 grams is to 32 grams. 4:32 is equal to 1:8. In previous discussions, we made that in H2 also, hydrogen and oxygen will be combining in 1:8 ratio also. Yes, the same ratio is maintained. In the previous case, or a multiple of it is followed. In this case, same ratio is maintained. Let us take the third example. As this is a typical example, I am going to discuss this many times with large number of examples. Hydrogen and oxygen combining with sulfur. Hydrogen combined with sulfur to produce H2S. The mass ratio is given 32 grams of sulfur combined with 2 grams of hydrogen. Similarly, in the other case where sulfur dioxide is formed, 32 grams of oxygen combined with 32 grams of sulfur. So, in both cases, I fix the weight of sulfur. Weight of sulfur is fixed 32, and I compare now the weight of hydrogen that combine with oxygen to produce water will be the discussion. Let us take the first weight ratio. It will be 2:, as sulfur weight is fixed, weight ratio of hydrogen and oxygen combining with fixed weight will be equal to 2:32. I am taking this ratio. The weight ratio of hydrogen and oxygen in H2O is 2:32. The weight ratio of hydrogen and oxygen in H2O is 2:16. This value is obtained from this data. This value is obtained from this. hydrogen and oxygen to combining to produce water. From the direct combination of hydrogen and oxygen, the second data is taken. If I take the first ratio is 2/32, the second ratio is 2/16. If I take the ratio of these two, it will be 1:2, which is a simple ratio. So, with the help of 3 examples, we made a discussion, and one example is given for you for solving. Please look into the data. Nitrogen and hydrogen combine to produce ammonia. This is the case taken. Other thing is hydrogen and oxygen combine to produce water. Hydrogen weight I can fix. Based on that, if at all nitrogen and oxygen combine, what could be the ratio combining? Is it going to illustrate law of reciprocal proportions or not? Law of reciprocal proportions, often called as law of equivalent proportions also. Later, while discussing equivalent weight concept, we come to that. What is the data given? Please verify. In the combination of ammonia, nitrogen percentage, hydrogen percentage is given. In the combination of water, oxygen percentage, hydrogen percentage is given. In N2O3, nitrogen percentage, oxygen percentage is given, and the question asked by him is prove that the law follows, that data follows law of reciprocal proportions. Based on the data given, please verify. In the first case, if you want once, you please go through the data given. Nitrogen hydrogen combining ratio is given, hydrogen and oxygen combining ratio is given. In N2O3, this product nitrogen oxygen combining ratio is given, 3 data is given. You are asked to prove the law of reciprocal proportions. So, the same data I used. 17.68 grams of hydrogen is combining with this much grams of nitrogen. I calculated per 1 gram. Per 1 gram, how much nitrogen is going to combine. Similarly, what I do is, in the second data also, 11.0 grams of hydrogen is combining with 88.9. So, 1 gram of hydrogen combines with how much amount of oxygen? I made the calculation. So, if at all nitrogen and oxygen are going to combine to produce dinitrogen trioxide as given in the question, please observe here N2O3 is the product to be produced. So, to produce N2O3, what will be nitrogen oxygen ratio? I need to make the calculation. So, in these cases, nitrogen and oxygen ratio will be 4:4.7:8.01, which will be equal to 1:1.72. From the experimental data which is given, in N2O3, this much nitrogen is combining with this much oxygen. So, 1 gram of nitrogen is combining with how much? 1.7. The same ratio will be maintained. Hence, I can propose that this data is in support of law of reciprocal proportions. Okay, right. Now, till now the 4 rules we discussed, 4 laws we discussed. Law of conservation of mass, law of definite proportions, law of multiple proportions, and law of reciprocal proportions. All these laws deal with the masses of the materials, means that the weights of the substances are taken for study. Now, we are going to propose a law which is based on volumes, that is law of gaseous volumes. Often this is simply called as Gay-Lussac's law also, this because it is proposed by the scientist Gay-Lussac. According to him, in a gaseous reaction, whenever reactants combine, gaseous reactants combine, they combine in a simple ratio. They also bear a simple ratio with the product if the product is also gaseous. Means that, very simple logic I am taking here, nitrogen combining with hydrogen to produce ammonia. Please remember that reactants, both the reactants are gaseous and the product is also gaseous. Nitrogen is a gas, hydrogen is a gas, the product ammonia is also a gas. Now, according to this law, if these two are gases, one volume of nitrogen combined with one volume of hydrogen, please do remember that to propose this, the equation is to be balanced. To have a proper understanding, the equation is to be balanced. N2 plus 3H2 gives rise to 2NH3. The stoichiometric quantities I am going to write here 1, 3, 2. These are usually called as stoichiometric coefficients. I also call it as stoichiometric order. This is necessarily to be followed in any chemical reaction. So, one volume of nitrogen will combine with 3 volumes of hydrogen producing 2 volumes of ammonia. 1 volume of nitrogen gas combined with 3 volumes of hydrogen gas producing 2 volumes of ammonia gas. Please remember, with the products you can establish the relation only when the product is also gaseous in nature. First condition, this is applicable to gaseous substances only. And second condition, this rule is strictly applicable. This rule is strictly applicable when the volume measurements of all the substances are made under the same temperature and pressure. At whatever temperature and pressure nitrogen volume is measured, under the same condition hydrogen volume is also to be measured, under the same condition ammonia volume is also to be measured. Then only this law will be applicable. Okay. Whenever gases combine, they do so in fixed proportion by volume. Okay. They bear a simple ratio, and if the product is also gaseous, that product also bear a simple ratio with the reactants. Right. For that, just a simple example will be taken, hydrogen combining with chlorine to produce HCl. For this, please make a balanced chemical equation. You can have a proper idea. H2 gas combining with chlorine gas producing HCl gas. H2 plus Cl2 gives rise to 2HCl. Please remember, the proportion is to be 1:1:2. Okay. This is, I am going to call it as a stoichiometric order. Hydrogen volume 1 volume, chlorine volume 1 volume, and hydrogen chloride produced will be 2 volumes. This gives us one advantage. For example, what is this volume? This volume can be milliliter, this volume can be liter, this volume can be gallon, anything can be taken as a measure of volume. For example, if I am taking 1 milliliter of hydrogen, will combine with 1 milliliter of chlorine to produce 2 milliliters of HCl gas. Same thing, if I am taking 1 liter of hydrogen combined with 1 liter of chlorine to produce 2 liters of HCl gas. So, by any quantity you can raise this, that volume refers to any scale that can be taken. Please look into this second example, nitrogen combining with hydrogen to produce ammonia. According to this balanced equation, nitrogen 1 volume combined with 3 volumes of hydrogen, that will be producing 2 volumes of ammonia. Please make the observation here, this volume can be taken 1 liter of nitrogen combining with 3 liters of hydrogen producing 2 liters of ammonia, like that. I can raise this quantity by any proportion. For example, 1 into 22.4 liters can be taken. It will be 3 into 22.4 liters can be taken, and the product produced will be 2 into 22.4 liters. So, ammonia produced will be 44.8 liters when I am taking by this proportion. Okay, that is the advantage of this. But this rule while applying, you need to be very careful. As I told you, the volumes are to be measured under same conditions of temperature and pressure, and this is also applicable to gaseous reactions only, because volume measurements are made. Not applicable to cases where solid is one of the reactant or product. For example, here ammonia combining with HCl to produce ammonium chloride solid. As this is a solid, you cannot propose Gay-Lussac's law for this. So, either the reactant is solid or the product is solid, you are not permitted to apply that, because solid volumes and liquid volumes are completely different. This law is applicable to gaseous reactants and gaseous products only. Right. Now, we make some illustration here. One example can be taken. For the gaseous reaction, hydrogen and chlorine combining to produce HCl, a balanced equation is given. If 40 ml of hydrogen is completely reacted with chlorine, means that chlorine is taken in a large excess quantity, so that all the taken hydrogen is completely getting reacted. So, this is in a larger quantity that he did not mention. We need to understand the content while reading the question. Hydrogen completely reacted, meaning that will be possible only when this is quantity is exactly or greater than the quantity that is required. So, this is in a large excess taken, so that all hydrogen can be converted into HCl. Now, the question will be, find out the volume of chlorine and volume of produced HCl. How much quantity was taken? 40 ml was taken. So, first I produce the stoichiometric order. As I told you, 1 mole of this combining with 1 mole of this for the reaction to completely occur to produce 2 moles of HCl. I will be calling this as stoichiometric order. This order need to be followed. So, first I write the stoichiometric order. Based on that, I propose a relation 1 ml combined with 1 ml producing 2 ml. Suppose instead of that, I am taking 40 ml of hydrogen should combine with 40 ml of chlorine to produce double the quantity, because it is 1:1:2. So, 80 ml of HCl will be produced. So, volume of chlorine required will be 40 ml. Volume of chlorine required will be, for the complete reaction, volume of chlorine required will be 40 ml and produced volume of HCl will be equal to 80 ml. And one more point we need to consider here, Avogadro's law, a very famous law. Equal volumes of gases contain equal number of molecules at the same temperature and pressure. Equal volumes of gases under the same conditions of temperature and pressure contain equal number of molecules. Please remember, hydrogen combining with chlorine to produce HCl, 1 volume, 2 volumes will be produced. Suppose if this is containing n molecules, 1 volume is containing n molecules, this will be n molecules, this will be 2n molecules. Suppose if I am taking half molecule, this will be half molecule, this will be 1 molecule produced. This rule actually, if I am taking half molecule of hydrogen, meaning that 1 atom will be taken. I write here half H2 plus half Cl2 gives rise to HCl. Half molecule combining with half molecule of chlorine to produce 1 molecule of HCl. So, this law made a proof that molecules are divisible. What is half molecule? Half molecule is nothing but 1 atom of hydrogen combined with 1 atom of chlorine to produce 1 molecule of HCl. So, this law, Avogadro's law, made a proof that molecules are divisible, they will be converted into atoms. Based on that, Avogadro made a proposal that atoms are the fundamental particles of matter. Now, for all the stoichiometric calculations, we need some basic information that I want to give you, because this will not be given in the initial discussions related to mole concept. So, it is to be separately learnt. Earlier we used to have this discussion in states of matter. The topic is not included now, it is deleted from the syllabus, but in all the stoichiometric calculations, this basic information we require. Okay. So, additional information for understanding Avogadro's law: 1 mole of each gas at standard temperature and pressure. Standard temperature and pressure is often called as STP. Standard temperature and pressure, this is usually called as STP. Okay. Have same volume. where standard temperature will be 273.15 degrees Kelvin or 0 degrees centigrade. The volume occupied by 1 mole of any gas at STP is called as molar volume. So, this is one more important statement we need to remember. What is molar volume? Volume occupied by 1 mole of any substance. At STP, molar volume of the gas is given as 22.71, 098 liter mole inverse. Usually for all the calculations, it will be taken 22.7 liter per mole inverse. Okay. But the problem is no problem solving, or when you refer the books, usually instead of 22.7, it is taken 22.4. The reason for this will be the temperature is 273.15 and the pressure is taken 1 bar condition, which is the SI system. 1 bar is taken. Under that condition, gram molar volume will be 22.7. But usually the books follow the old convention. Old convention means temperature will be taken same, 273.15 Kelvin or 0 degree centigrade. But while pressure is taken, they take 1 atmosphere. 1 atmosphere will be taken by them. As 1 atmosphere is taken, there is a slight change in the calculation. I am going to get 22.414 liter mole inverse, or it will be taken as 22.4 liters. So, majority of the books, majority of the teachers and majority of the calculations will take only 22.4 in all the calculations, but its original value according to IUPAC should be taken as 22.7. Okay. In the NCERT textbook, whatever convention is given, you please follow that. And a small information related to that will be, however, in stoichiometric calculations, it do not make much difference in the result. So, in the calculations, whether you take 22.4 or 22.7, near answer for all the objective questions will be not going to change much. Yes, there is one more condition, standard ambient temperature and pressure, that is often called as SATP. SATP, standard ambient temperature and pressure, and the temperature will be 25 degrees centigrade. Why only 25 degrees centigrade? That is the room temperature, European room temperature is 25 degrees centigrade. So, that is fixed as a standard by IUPAC, which refers to 298.15 Kelvin. And in place of pressure, they will be taking 1 bar, which is equal to 10 power 5 pascals. Under that condition, the molar volume of the ideal gas is going to slightly change, 24.787. Instead of 22.4 liters, SATP condition if taken, we need to remember this 24.789. Usually, this based questions are not given in our syllabus, but for an information, you please remember this is a thermodynamic condition. The SATP is usually a thermodynamic condition. Under that, the molar volume value will be slightly different when compared to the gram molar volume what we discussed previously. Okay. With this, we are going to conclude the discussion related to the laws of chemical combination. With another topic, mole concept, we will discuss in the next class. Thank you.